Today, we'll be discussing permeable pavement, a topic presented by Marty Wanielista as part of the BMPFast series. Permeable pavements are a significant option for stormwater treatment, primarily through retention. They are commonly implemented in areas such as parking lots and, increasingly, in sections with light to moderate traffic flow. To date, their aesthetic appeal and their effectiveness in removing pollutants through retention have proven quite acceptable. In fact, many consider permeable pavements to be an excellent best management practice, or BMP, partly because they are often economically feasible to implement. In this module, our learning objectives will focus on understanding permeable pavement systems. We'll begin by defining what permeable pavement is and exploring its different types. A key aspect we'll cover is how the reservoir beneath the pavement stores stormwater runoff before it's removed through exfiltration. It's important to distinguish exfiltration, which refers to water moving into the ground from below surface storage, from infiltration, which is water moving directly into the ground from the surface. We will then navigate the BMPFast software, learning how to enter data for annual mass removal analysis and interpret the output specifically for permeable pavement applications. We'll also demonstrate the practical use of its various worksheets. A significant benefit of these systems is their role in protecting groundwater. We'll learn how to calculate the quantity of groundwater recharge in terms of million gallons per year. Furthermore, if sorption media is used, the software can calculate the reduced average annual concentration of pollutants. To bring this all together, we'll work through an example project, and finally, we'll learn how to save our data in the BMPT file format. Permeable pavements serve as an excellent example of a low-impact development, or LID and green stormwater infrastructure, or GSI best management practice. These pavements offer both structural integrity and crucial water infiltration capabilities. There are several types available, including permeable or pervious concrete, flexi-pave, and various kinds of permeable pavers and permeable asphalt. When considering these options, it's always wise to contact local suppliers to determine the most sustainable void spaces available within both the reservoir and surface layers for your specific project. It's also worth noting that many of these permeable pavement technologies earned the H2O4U Certificate of Excellence back in the late 1990s, a time when such certifications were essential for advancing the consideration and adoption of these important best management practices. This slide emphasizes the progress in pervious pavement research and development, aiming to establish them as a new standard. Here, we observe a commercial parking area, where different types of permeable pavements are showcased. We also see a residential site, demonstrating how permeable pavement can be integrated around a pool and for a walkway. These examples clearly illustrate the many potential applications for permeable pavements. While their uses are diverse, they are particularly valuable for parking and residential needs, helping to reduce the ratio of impervious areas on a building site and ensuring compliance with local building codes. This particular site, located in the western panhandle of Florida, provides an excellent example of integrated stormwater green infrastructure. Notice the use of permeable pavement, which has been incorporated into both the parking area and some of the pedestrian paths. When designing such systems, it's crucial to carefully consider the loading on these permeable drives to prevent cracking and the premature loss of pavement integrity. Additionally, you can see several rain gardens strategically placed throughout the landscape. While not visible in this specific view, this site also features an expansive green roof, covering an impressive area of over 33,000 square feet, further contributing to its comprehensive stormwater management strategy. When installing permeable pavement, it's crucial that the contractor adheres to standard procedures. These include precise placement of the materials, making appropriate separation cuts, often referred to as pizza cutting due to the tool used, to control cracking and allow for expansion. Following these steps, a critical 7-day curing time is necessary to ensure the pavement fully sets and achieves its intended strength and permeability. Permeable pavements require regular maintenance to ensure their continued effectiveness. One common method for assessing when maintenance is needed involves using an embedded ring infiltration kit, often referred to as ERIC, if, when using this kit, the limiting infiltration rate is measured to be lower than 2 inches per hour, it's a clear indication that maintenance is due. Alternatively, a more visible sign that maintenance is necessary is when you observe ponding on the pavement surface for over half a day. Among the various maintenance techniques, vacuum sweeping is frequently employed. This method is particularly effective because it removes not only surface particles, but also accumulated debris and sediment from within the pavement structure itself, which helps restore its permeability. Here, we see our 3P puppy mascot diligently working, representing the crucial role of maintenance in cleaning up both personal and other on-site pollution, thereby ensuring the longevity and performance of permeable pavements. Here we're examining the quantity of solids collected after a 1-hour cleaning session as part of permeable pavement maintenance. The data distinguishes between 2 types of sediments that were removed. One pavement had a clear visual loading of sand before cleaning, which resulted in a collection primarily of sandy sediments. The other pavement, however, showed a visual accumulation of various debris, including finer particles like silt, and consequently yielded a higher quantity of fine-grained sediments after maintenance. Let's look at a practical example, adapted from an actual application, to illustrate the use and evaluation of permeable pavement. We're considering a medical plaza planned for an existing 2-acre general agricultural land use in Bradenton, Florida. This site is classified as high-intensity commercial due to the anticipated frequent traffic it will generate. The owner proposes to implement permeable pavers across all parking and roads, covering a significant 0.9 acres, which is 45% of the total area. And these areas are directly connected. It's also important to note that the building downspouts are disconnected from the pavement system, and the curve number for the non-directly connected impervious area is 60. The permeable paver section itself is designed with 4 inches of paver, 20 inches of rock, and 2 inches of pollution control media, specifically included to protect groundwater quality. This layered system provides a substantial 26 inches of reservoir storage. The project must meet a specific performance standard, addressing an impaired condition and being situated within an outstanding Florida water, or OFW. We will now take this project description and go directly into the BMPFast software to enter all of this data and conduct the analysis for annual removal. If you wish to hone your skills or learn how to enter data, I encourage you to open the BMPFast software and follow along, pausing the presentation as needed to allow more time for learning. At this point in our analysis, we would enter the specific data related to both the immediate site and the broader watershed conditions. If you're working with the BMPFast software, I encourage you to pause the presentation now and input this information yourself, as it's an excellent way to deepen your understanding and gain practical experience. A particularly important consideration for this section is the protection of local groundwater. We'll need to carefully calculate the average concentration and total loadings that might enter the ground from whatever retention option we ultimately select. Now let's look at how we input and analyze treatment data using our permeable pavement worksheet. We'll start by navigating to the worksheet itself, which you can access via the green button on the Treatment Options page. Once there, ensure you've selected Permeable Pavement as your media option. A critical parameter to note for this selection is that the residence time should be greater than 2 hours for effective treatment. Next, you'll specify various design elements, the particular pavement types you're considering, the specific pollution control media, and the reservoir rock support types along with their depths. As you make these selections, you'll observe that the storage capacity, measured in acre-feet, will dynamically update and display. Once all your parameters are set, simply click the Calculate button to generate the complete analysis based on your inputs. So, does the pavement meet the specified performance standard for OFW and impaired waters? Yes, it absolutely does. From the Permeable Pavement worksheet or the summary sheet, we can confirm that the pavement functions to remove at least 95% of the annual runoff volume. This successfully satisfies the required percentage removal performance standard. And looking at the second question, does the pavement also meet the net improvement standard? Again, the answer is a definitive yes. You'll note these affirmative responses are typically colored green, which, in this context, effectively means go, indicating we've met these important criteria. With the discovery option, you can utilize the plot button to investigate how annual removal rates change in relation to the storage or treatment depth. This feature allows you to see the impact of varying depths on the overall removal. In this specific scenario, both the predefined removal percentage and the targeted net improvement percentage were successfully achieved. Let's consider the impact on the groundwater. With the 0.9 permeable pavement in place, we observe a groundwater recharge of 1.06 million gallons per year, and the average total nitrogen concentration is significantly reduced to 0.96 milligrams per liter. These results can be found in either the permeable pavement worksheet or the main summary sheet. It's crucial to understand the benefit provided here. If this water were allowed to infiltrate without the advanced sorption media, the total nitrogen concentration would have been considerably higher. Specifically for developed land conditions, it would have reached 2.24 milligrams per liter, and for agricultural conditions, it would have been 2.29 milligrams per liter. These higher figures represent the event mean concentrations, or EMC values, typical for those land uses without treatment. Let's recap what we've covered regarding permeable pavement. We started by defining what permeable pavement is, exploring its various types, and discussing the necessary maintenance requirements. We then moved into the practical application, learning how to navigate the system and input data for annual mass removal analysis, and subsequently understanding how to interpret the output using the provided worksheets. Through an example problem, we demonstrated how permeable pavement can help meet performance standards. This included analyzing groundwater recharge data and observing the significant impact on groundwater total nitrogen, showing a reduction from 2.40 milligrams per liter down to 0.96 milligrams per liter. We also discussed how to save this data using the BMPT file format. Finally, we also explored the discovery option to understand the marginal change in average annual removal. This concludes our module on permeable pavements, presented here by Marty Evangelista as part of the BMPFast series. We encourage you to explore other learning modules to deepen your understanding and to apply to take the competency test. For specific details on the test, please refer to the learning module titled Self-Test. This work is supported by publications such as the final report for FDOT Project BD 52102, specifically Report 1 of 4, focusing on the hydraulic performance assessment of pervious concrete pavements for stormwater management credit, authored by Evangelista and Chopra in January 2007. Additionally, software developed by the Stormwater Academy at UCF is available to assist in design. You can download this Excel program by visiting stormwater.ucf.edu and navigating to the Research Publications section. Thank you for watching this presentation.